Here I'm going to talk about question number 7, which I decided to split up into two parts. In part A, I'll talk about why delta H is equal to the integral of Cp dt, while in part B, I'll talk about why Cp is used instead of Cv, since both processes can be reversible. And I interpreted part B to basically ask why we use Cp instead of Cv as a specific heat in the delta H integral. So to start off part A, again I'll discuss why delta H is equal to the integral of Cp dt. Throughout this entire video, I'll be operating under three key assumptions, mainly that the process is reversible, that there are no other forms of work beside PV work, and that work is positive if it's performed on the system. So first off, we'll start off with the first law of thermodynamics, which states that energy is conserved, which can be stated as a change in internal energy equals the change in heat plus the work done on the system. Now we'll use the assumption that we're operating with a reversible process to equate the change in work to negative PdV. Here we introduce enthalpy, which is naturally defined as the internal energy plus PV work. The definition of enthalpy can be extended to change in enthalpy, which is more meaningful, as dH equals du plus PdV plus VdP simply by taking the differential of both sides of equation number 3. You can notice that for equation 4 we can rearrange it in terms of change in internal energy, du. So we do this and plug it back into equation 2 and rearrange to get equation number 5, which is dH minus VdP equals change in heat, which gives us a useful equation in terms of change in heat. The equation we derive for the change in heat, equation 5, is in terms of the change in pressure, or dP, which is now circled in red. To rearrange for the change in enthalpy with respect to the change in temperature, which we'll use to get Cp, we'll want to take the differential at constant pressure to get rid of this dP. Doing so, we get equation 6, which is dH dt at constant pressure equals a change in heat with respect to dt at constant pressure. This change in heat with respect to change in temperature at constant pressure should be familiar to us, as it's the very definition for heat capacity, which is defined as the ratio of the heat added to or removed from an object to result in a given temperature change. Finally, we can rearrange equation number 7 and plug it into equation 6 to get our final equation that delta H is equal to the integral of Cp dt. After going through the derivation for delta H equals the integral of Cp dt, I'll talk more closely now about why Cp is used in the integral instead of Cv, although both processes may be reversible. I'll start this part off again with the first law of thermodynamics, saying that du is equal to delta Q plus delta W. Similarly, we'll continue again by plugging in negative PdV for the change in work. Except now we stop here at equation 2, noticing that we have an expression for the change in heat, but this one is in terms of the change in volume. So we'll want to get an expression for du dt, but to do that we'll need to take the change at constant volume to get rid of this dV. Doing so, we obtain du dt at constant volume is equal to the change in heat with respect to the change in temperature at constant volume. As in the previous derivation, we notice that the change in heat with respect to the change in temperature at constant volume is now Cv instead of Cp since we're at constant volume. Now rearranging equation number 4 and plugging it back into equation number 2, we get that the change in internal energy is equal to the integral of Cv dt. After seeing that Cp was used in the change in enthalpy equation and Cv was used in the change in internal energy equation, we see that this arises from the dP term in the above equation for dH and the dV term in the below equation for du. In conclusion, for part A, we derived delta H equals the integral of Cp dt based on the first law of thermodynamics as well as the definition of enthalpy, and we also showed that Cp is used for change in enthalpy instead of Cv due to the dP term in the definition for enthalpy.